So now here is how you go about finding velocity of some particular point on the inclined part of the string. So it's a very interesting case. We are going to be borrowing ideas from the chapter of rotational motion, rigid body dynamics. See, it's very interesting. Although string is not a rigid body, the string can bend. Right? So string is certainly not a rigid body, but as long as the string is going to be moving in the configuration of the pulley, it is going to be a taut string, which means that the separation between you take the end of the string and point C, the separation between those 2 points is not going to be changing. So that is the idea we are going to be using, and we will borrow ideas from that of rotational motion chapter to find velocity of point C. Now, how to do that? I'll just give you the method quickly, and then also I'll tell you the logic behind why we are doing this. Now, suppose say the distance of point A from the pulley which is shown, point A meaning the end of the string. So from the pulley till the end of the string, let's say that length over there is L, and from the pulley to point C, let's say the length is L by 2. I'm just assuming a point C like that. Then along the length of the string, point C's velocity over there, that will be v cos theta, and perpendicular to the length of the string, the velocity will be v sin theta by 2. And along the length of the string, it is going to be v cos theta, and velocity of point C will be vector addition of v cos theta and v sin theta by 2. So vectorially, you add these two components, that will give you the velocity of point C. Right now, if you are going to kind of pay attention to the orientation of the string, the pulley is over here, a small pulley. After some time, the string is going to be in this particular orientation. Note that the end of the string is connected to the block. If I call that end as A, so point A is moving in a straight line. It has moved from A to A dash. But if you consider a point C over there, that point C would have moved in some particular curved path and not a circle per se. Okay, it moves along some curved path, it would have moved, and it has reached point C dash. Right, and note that the orientation of this string that keeps on changing as the block is going to slide on the horizontal table. So what we are going to be saying is the point which comes into contact with the pulley on the string. So just I'll draw one diagram to indicate that. See, suppose that this is the pulley, right? And the string comes into contact with the pulley at some particular location, and where it comes into contact, the string will be tangential to the pulley. So then the velocity of the point on the string over there, that will, in fact, for each and every point on the string, this component of velocity, that is going to be v cos theta, and the point where the string comes into contact with the pulley, the string is going to be in a tangential orientation to the pulley being a rigid object. The point which comes into contact, that cannot move in this direction, so there will be no velocity perpendicular to the length of the string. That point will have zero velocity. So place an observer over there. um, this is the idea of kind of instantaneous center of rotation problems that are done in rotational motion. So if you place an observer at the point where the string comes into contact with the pulley, that particular point has no velocity perpendicular to the length of the string, and as seen by that particular observer, every point on the string at this instant is going to be moving in circles. So if this distance over here, if this distance is some x1, the end of the string, and you take some other point on the string at a distance of x2, then the point which is at a distance of x1 as seen by that observer will have velocity perpendicular to the string x1 omega, and the point which is at a distance x2 will have a velocity of x2 omega as seen by that particular observer. And since I have considered a case where A is at a distance of L and C is at a distance of L by 2, so point A has a velocity v sin theta perpendicular to the length of the string. So point C will have a velocity of v sin theta by 2. It's basically L omega and L by 2 omega, right? So v sin theta and v sin theta by 2. So that's how you get the velocities of different points on the string over there. I know how to get this particular omega. If v and theta is given and the length of the string is given, you can go about getting these values, right? So that's how you should be approaching to find velocity of some particular point on the string. Okay.